presentation. Thank you very much. I like pretty good short too.
I don't know why you jumped so fast in 5 minutes.
Well, I guess I'm going to have to repeat it all then for everyone. In case you didn't catch, my title is The Behavior of Rotating Magnetic Microbots Above the Step-Out Frequency with an Application to Control Multi-Robotic Systems. Try saying that 5 times fast. This was a paper done by multiple professors, including Jake Abbot. And being very short, this is about microbots. Yes, we do have medical microbots. In a 2012 IEEE article, they talked about 3 of them that are currently being used. A drill, a camera, and also can be doubled as a capsule at times, and kind of a giant shovel. These are moved through an MRI. I'm going to be covering a lot of detail quickly, so I'm going to first talk about how an MRI works. The MRI normally works by using a combination of magnets to excite, or as they put, it aligns the spinning protons in the body. There you have the RF coils transmit radio waves that at a certain frequency will allow the rotating protons to flip 90 degrees. When this occurs, the MRI turns off. And this allows, well, the magnetic field turns off, and this allows the protons to go back into to a less excited state. The energy that's released then goes back to the MRI machine, and it's able to determine what was the tissue type, whether it was bone, whether it was muscle, whether it was brain or anything. So how does that work on our robots? We've seen horror movies where you put a magnet and they have some kind of metal figure in it and it rips through them. How does that not work in an MRI machine? That's because the main magnet, when it's turned on, will create a uniform magnetic field, which doesn't pull the robots out, but it aligns them rather than pulling them out. Then using those RF coils, and slight tugs from them, you can move the robots in any general direction. This will allow them to move through veins, arteries, even to the small capillaries, depending on how small the robots are. Now we have a problem. This magnetic field will affect all the robots and move them uniformly. This is not good when you want to inject a person with robots at a certain site and then disperse them throughout the whole body. So the problem of this paper is, how can we solve this? How can we move this multi-system of robots that are controlled with a uniform magnetic wave non-uniformly? This wasn't supposed to last as long. Maybe I got stuck. Oh, never mind. The solution is we are going to be using what's known as the step-out frequency. The step-out frequency is effectively converting the rotating magnet field into differential displacements. But the step-out frequency's actual definition is the field rotating frequency where the magnetic torque is not strong enough to synchronize with the microbots with the field. So the microbots themselves have a type of material in them, whether they are permanent magnets or soft magnets that can be magnetized. These different elements can be pulled by different frequencies in the magnetic fields. This paper does a great job at outlining the angular velocities and the step-out frequencies for both permanent magnets and soft magnets. This is a little drawing they did about it. A and C are permanent magnets, and C, B, and D are soft magnets. And basically what happens is when you apply this, when the frequency of the magnetic field is outside the step-out frequency, it causes a moment around the magnetic dipole. This allows them to move in a different amount than what their counterparts of a different magnetic property are going to move. For a brief demonstration, we have 2 different magnetic step-out frequencies above. One as 1 Hz and one as 7 Hz. This regular type, which is N42 material, creates a box, while this N52 material creates a much smaller box. When we go to a larger frequency, the 42 material is roughly the same, but that 52 material is now no longer doing a small box, but a giant box. This is just one of the major steps forward to be able to control these large, complicated, multi-robotic systems. And the great thing about this paper is it was successfully able to determine the step-out frequencies of these microbots, and is an important step forward and how to control multi-robotic systems when they're that small and being controlled by something other than a motor or other outside sources. That brief slide was my sources. I've already mentioned them in my talk. Thank you very much.